everyone again, and welcome to the last session of the NB-IoT and LTE-M Learning Week. Today we have a real, last but not least, type of session. So we will do a deep dive in non-IP data delivery with Acklio. So briefly about Acklio. Acklio brings the IP-based communications to the IoT networks to provide new capabilities to the emerging IoT networks like NB-IoT and LTE-M, but also LoRaWAN and webhooks. And today they will present us, from the other side, they will present us the non-IP data delivery. And with that, how can we reduce the traffic and boost the energy while providing security? So I believe it will align perfectly with our yesterday's session on IoT security and today's session on different IoT protocols. And I'm very glad to have our speakers with us today. So we have Alexander, he's the CEO of Acklio, and we have Hussein, he is the standardization and research engineer of Acklio. And with that, I would like to thank once again to Alexander and Hussein and hand the word over to them.
Thank you very much, Yanni. It's a real pleasure and thank you very much for your invitation. Hello, everyone. So as we said, my name is Alexander Pelov. I'm CEO and founder of Acklio. And today we are going to, so we are at the last session, but as always, the best is for the end. So I hope that we'll be able to you'll be able to gain some deep knowledge about what's coming for non-IP data delivery and in general for NB-IoT in the forthcoming months. So before we dive in the topic, I would just like to give you a brief introduction of about Acklio. So who we are and what we do. So we are a software company. So we are an inventor of the core technology that's behind the SHIC technology. We're going to be talking a lot about this. So SHIC stands for SCHC, so static context cluster compression. But we'll be talking about this further on. So we're a French company. We are a spin-off from one of the biggest engineering schools, and the fruit of our products and of our technology is a fruit of 20 years of R&D projects and 13 PhDs that were defended on that topic. So we are an active member, and we have really taken it to our hearts to go and standardize the technology, because we believe that security, interoperability, and energy efficiency are a major challenge and a major opportunity. And the only way to actually spread the world is through standardization and through helping the world adopt this technology. So having said that, I would like just to say that everything that we say here has actually already been adopted and implemented in many communication modules, in many in meter manufacturers. It was deployed. So it is a tested technology, right? We're not talking about science fiction, even though some of the things we're going to be presenting may seem like too good to be true, but it's actually real things, right? So we actually do have real meters. So here, you know, I as a software, and let me just then click this little feature here. As a software guy, I really actually like hardware, because it's a real thing. So we have the real SHIC technology here running. So that's a smart electricity meter that's been in operation for more than 2 years and perfectly well. And that's a water meter. Like, it's a water meter. So we are actually, on one hand side, very interested in doing optimizations, but also in battery life. So this is what we're going to be talking about today. And just to give you an idea of what we are doing to actually make sure that everything works. So we make software. We make part embedded software and part network software. They plug in seamlessly in any type of existing communication technology. So be it NB-IoT, any NIDD or IP, or LoRaWAN or other technologies. And the embedded stack goes in the communication module or in the device. It's extremely low footprint. So it can be less than 40 kilobytes with all features enabled, flash, and 2 kilobytes of RAM. Right. And the IP core, so this is the core server that connects behind the network infrastructure. It super scalable. It can be installed on a gateway, or it can run in the cloud, and it can handle millions of meters or millions of devices. Now, end of this short introduction of why the technology is here and that it's actually something that's really working. I would just want to go and do a step in the direction of why IP and why non-IP, right? Because that's actually the crux of the question. Why would we like to keep the good benefit, the good things about IP, and why would we like to do non-IP, right? So on IP, there are many things actually. I think that we can do like several seminars just on that. And here I'll just try to say it in less than a minute. First thing is interoperability. So the whole internet works on IP, and IP is the abstraction layer between communication technologies and application and services. And if you remove IP, you need to do a lot of engineering to actually be able to get the two fit together. And every time you want to move one, you need to be able to, you need to change the other in some way or the other. So it becomes a tightly coupled system. So IP solves that. So that's the first thing. Then the second thing is that it's actually a solution that works, and that has been working for very long time. So 40 years and counting. So I challenge anyone to tell me an API that has been out there for more than 40 years, more than 20 years, or more than 10 years, and that has not changed in a radical way. So IP gives this socket, this foundation of stability around which you can build infrastructure. And it's going to be here for many decades to go. And when you deploy a critical infrastructure, then you want to be sure that the thing is not going to just, well, you need to rewrite the whole thing in 10 years down the road. And of course, you have all these established end-to-end protocols, frameworks, existing ecosystems, and they have been here for many years. And how do you do that? Right? So very interesting properties of IP. Non-IP, on the other hand, it also has, it solves some of the things that original IP could not do very well. The first thing is, and first and foremost, energy efficiency, and all kinds of efficiencies, but energy efficiency. With non-IP, we can really go to almost to the physical layer and get all the possible optimization, scrap every microjoules or microwatt hours of energy, and be as efficient as possible. So that's really good. We really love that for battery operated devices. You can also have higher density. So you can really deploy many, at very high densities around a cell. So that's really great. Right? And if you want to send a few bytes, then the signaling part around that in IP could be like a lot, really a lot. And you don't need to set up the IP part, the security configuration, and so forth. So the question here, of course, is, can we get the best out of both worlds? And the reason of our existence and why we actually did all the work around SCHC was to do exactly that, be able to combine both. So what is SCHC? The static context header compression, so which is called SCHC. So that is a compression and fragmentation framework. It is an adaptation layer that was standardized in April 2020 under RFC 8724. So that is the foundation of this framework. And since then, there have been other RFCs that came to complete that framework. And what it does is, well, it allows to compress to a very significant amount all the protocol data in the protocols themselves, so that they become super efficient. In that way, you can have the same efficiencies of IP protocols, the same level of efficiency as non-IP approach. And there is actually the NB-IoT RFC that is coming. So it is still in the last stages of the draft status, at the LPWAN working group at the ITF. So if you want to, you're invited, you can go, and it's really beautiful written text. So we're going to be talking about SHIC, what's possible, how you deploy it, and actually what you can get out of it, right? And that may come as a surprise to some, because typically, if you're talking about, well, NIDD and how would that work, and how would NB-IoT work, and so forth. So this is not going to be today a talk about you know, the different ways in which you need to interface your application with the SCEF, or I mean the other parts of the 3GPP network, or how actually the radio will work. What we say here is that there are so many optimizations that are already present in NB-IoT and LTE-M that actually really the urgent thing to do is be able to use them in the simplest way, and to be able to build services on top of them in the easiest and most interoperable way. And for us, SHIC is the solution for that, and SHIC and IP. Crash course in how SHIC and how IP works is on this slide. So this is like the 10,000 meter view of how SHIC works so damn good. So each of the lines here represents an IPv6 packet. So it's IPv6 and UDP, and then you have co-op and others. And if you look at the different, like if you step back and look at them, well, you have a lot of these fields, a lot of these bytes that never change. They're the same. Other, they change once or twice for the whole exchange, and that's it. So if you look at this in a very detached way, you can say, well, I can just build a dictionary, and with that dictionary, I can put part of the same dictionary on the device and in the network. And then instead of sending that every time over the air, well, I'm just going to send one indicator to say, hey, well, you know, just send value A, and the value can be a huge value, but just send it, and then it will compress to 1 bit. And that's the whole point. And that's the difference between the rough difference between IP and non-IP. Like in non-IP, people say, hey, well, we'll just remove the whole overhead of the protocols and IP and UDP and all these protocols. We'll remove that overhead because it's always the same, right? And here we are saying, well, there is this standard compression way to do that. And well, in the end, over the air is the same solution, but from point of view of system view and system architecture, you're still living in the IP world. And that has huge consequences. And I think that we'll be able to show that. Now, we're coming to the inevitable stage where there will be like a ton of abbreviations. And here the point is that we're probably not going to go into huge detail in each of these elements, but is to say that all this information you can read in detail in the draft. So it's a publicly available draft. You can go and read it today. And we're not going to go through all the possible paths in which an IP or non-IP packet can go within the core network, through the core network. But we're going to provide you with specific results of how the SHIC solution applies. And that SHIC solution works, and that SHIC and IP solution works in any of these cases, right? So with this, I'm giving the word to my colleague Hussein.
Thank you. So as Alex was saying, what we see in front of us is a simplified architecture composed of several entities. We have the user equipment. The user equipment will communicate with the evolved node B over the radio. So here we do not want to talk a lot about the radio because we are talking on upper layers. We have the MME, or the mobility management entity, which is responsible of signaling and other stuff. We have the CSGW, which is the cellular serving gateway, responsible of forwarding packets. We have the PGW, which is the packet gateway, which is actually responsible of allocating the IP after the attachment of the user. Of course, we have still other entity as HSS, or the application server, which we will highlight their role when it comes. So actually, we will start by one of the paths that is followed by a packet when sent from a device, and we will start with IP. So suppose that we have a device that uses IP-based NB-IoT, and this device wants to send data to a certain application. In order to do this, there are several steps. First, the device should attach with the network. Second, it obtains the IP, and this is, as I said, from the PGW. After obtaining the IP, the device needs to retrieve the server and connect with it. Of course, we need always secure communication. So in order to do this, several handshake messages have to be done. And afterwards, the device is capable of sending data on the radio to reach the application. And after doing this, it will disconnect. Now imagine that the device wants to send only 5 bytes. To do this, the device has to do all the steps that I mentioned. And let's suppose that we are using the DLS with UDP and IP. So what will happen is that the device will need to send 63 bytes. Why 63 bytes? Because we have 40 bytes for IPv6, we have 8 bytes for UDP, and we have 13 bytes for a typical DTLS. So imagine that for sending 5 bytes, you need to send this amount of data. Now, let's see the case of non-IP or non-IDD. Once again, the device wants to send 5 bytes of data to the application. So to do this, in this case, it will benefit from NAS, non-access startup, to send data over signaling. So what we are doing is sending data over signaling to the MME, which will encapsulate and send to the SCIF. So the steps are first attached to the network and then sends the 5 bytes of data. And it's only the 5 bytes. Afterwards, it will be disconnected. So as you see in this case, we are benefiting from only sending the required data to be consumed by the application. However, we are losing the interoperability provided by the IP layer. So here goes back to the question highlighted by you, Alex. Which one we need to choose, IP or non-IP? But before this, let's actually highlight some of the pain points in NB-IoT deployments. So what we did is that we exchanged with several stakeholders in the that are using NB-IoT, and we have a lot of or several challenges and pain points faced by operators, module makers, and others, and we are presenting some of them in front of you. So the first thing is latency. So latency is a major issue, especially in bad radio conditions, because this will lead actually to failure of handshakes or connection establishment and failure of transporting high volume of data. Another issue is that although NB-IoT is very rich in many kinds of features related to energy efficiency, to NIDD, to data over NAS, they vary significantly from one deployment to another, from one country to another. Now to focus on challenges related to IP, as mentioned by Alex, IP is a little bit power hungry, so you need to send at least 48 of bytes only as headers. And in case of having a radio condition, you cannot, or TCP TLS connection would fail. So this is a major issue for NB-IoT when having bad radio conditions. In addition, we have firewalls that might limit UDP connection, and NAT and PAD can also put some limitation in connections. Moving to NIDD. So NIDD is very good in terms of energy efficiency, but as I mentioned, the problem is with interoperability and with having protocols that would work directly over it, especially when we talk about high deployment or high volume deployment. So in order to get the best of these two worlds of and non-IP, we propose SHIC as a framework that not only unified them, meaning that you can have IP and non-IP at the same place, but also provide each one with a benefit and solve several problems that they are facing. So at Acklio, we proposed a solution, and the solution is aims at providing energy efficient, interoperable, and secure communication over NB-IoT. And to do this, we have two main components. First, make use of SHIC, specifically for the compression. So we will actually use SHIC to compress headers of IPv6, of UDP, of DTLS. We can go a step further by compressing the payload, and we propose and use an optimized version of DTLS. This optimized version actually first optimize the handshake procedure. This is one component. Another is to support high latency. So we have the timers that are adapted. We have the interval of handshake to be controlled according to the message number. And we support the connection ID, the CID functionality. So these are the components of the solution that we will present next. And what are the benefits? So I will summarize the benefits, then we will go to the implementation, and afterwards we can go to the numbers. I know that you want number to see how much we achieve, but let's us first see some benefits that are not or cannot be expressed in terms of numbers. So first, regarding an IDD, it will become IPv6 compatible. So we will have IPv6 over an IDD, but without losing any energy efficiency related to an IDD, meaning that an IDD will remain energy efficient. And actually, this is thanks to SHIC that will compress most of the headers related to IPv6 and UDP. Second, an IDD does not have the problem with the pattern net, so we do not have any problem here, and we will have reduced handshake overhead. Third, SHIC will help to compress the packet, so we have less latency and thus less probability of packet loss, less time on air, and thus higher energy efficiency. Now, regarding IPv4, SHIC with IPv4, our solution with IPv4, our solution will provide end-to-end communication, IPv6 communication over a public network, a secure one actually, a secure one, but an optimized one so that the traffic is reduced, so time on air is reduced, and thus energy consumption is reduced. So let's now go into the implementation where Alex will explain about the protocol stacks.
Thank you very much, Hussein. And so having said that, of course, we everything that we do is based on the SHIC standard. So and if you want to read more about how this vision is constructed, you only need to go to read the IoTM drafts. The first thing to observe is how do you build a service based on IP stack and non-IP stack. So it's a very simplified protocol view. So you see on the left-hand side the reference stack. So we have IPv4 with UDP and the application on top. And for NIDD, well, you have like the non-IP, and then you have the application direct on top of it. Typically, then people say, well, you put lightweight M2M on top, or like a very specific protocol that was specifically designed and built to support NIDD, and your questions or troubles are solved, right? Then the point is, of course, how do you do that for a more generic framework? But let's move from there on to see how we actually unify all that. The first step is to actually put SHIC on top of the NIDD layer, which you can use to introduce the IP and UDP and like up the layers on top of non-IP. So you have the exact same reference stack on both hand sides. And here it comes for a virtually zero overhead. Then, of course, it would all be very beautiful and nice, and it will be very, very sufficient 25 years ago when security in the internet was not really an issue. But today it's completely out of the question to deploy a solution that does not provide a security layer. So this is where you actually need a security protocol or a security layer to be able to have an end-to-end security between the server and the device. And typically that is something that it's a strong requirement. So DTLS is the layer that was, of course, standardized for many of these uses. Now, based on that, what you really want to go further is to have this end-to-end IPv6 addressable secure application stack. And here there are actually two possibilities. One is the way it works over existing IP, IPv4, for example, that will suffer NAT traversal problems, firewalling, and all these kinds of issues, right? But you want to have this end-to-end connectivity that is not affected by that you can have stable end-to-end IPv6 addresses, and you know, like you don't have losses whenever the middleware, whenever the network is starting to drop packets in the middle, right? So we have this very nice and clean end-to-end IP connectivity, IPv6 connectivity that doesn't change, right? Then you have the optimized DTLS version that Hussein was talking about that is secure in both ends of the communication. And then like beneath of this non-IP or IPv4. Here, the important part is that in the part above the DTLS, so it uses IPv6 and UDP, but these are compressed thanks to the SHIC. So here we have the SHIC compression actually in two places. Outside the encryption layer, outside DTLS, which optimizes and compresses the outside protocols, compression of the DTLS headers themselves. And then inside, we have the SHIC compression. So actually, look from far away, you can say, whoa, well, there are a lot of things that are stacking up. You have like huge overhead. But over the air, actually, all these layers are invisible. They take zero overhead. But they are very well present in your system design, in the way you deploy devices, in the way you develop software, and in the end, the way applications talk to the head-end system, applications talk to the servers. It's just that we compress that, and the SHIC compresses them in a super intelligent way, compatible with the internet. We can actually go one step further for that fully optimized operation, where SHIC actually compresses the application payload. And that becomes really powerful. And we have lots of use cases, for example, for DLMS. DLMS is a smart metering protocol that has hundreds of millions of smart meters already deployed. And it compresses of the order of 50 to 90%. So in the end, you have all these stacking up that results in payloads of the size of, I don't know, 10, 20, 30 bytes, completely secured, interoperable, end-to-end, solving all the NAT traversals issues, and where we can go from non-IP to IP, and that's completely transparent and completely fully compliant with the way a smart metering infrastructure needs to work. So I think I spoke long enough. And I know that you want to see the numbers. How much does it consume in terms of energy consumption when you use these energy optimizations? If I have a water meter running on NB-IoT, what will I get? If I use IP or non-IP, how much battery life will be improved? And for that, I'm leaving you in the hands of Hussein.
Oh, they have to wait until I explain how we actually implement it. So, okay. So what we do is that thanks to the collaboration with the Nordic Semiconductor, we implemented the solution that we described in the NRF 9160 low power SIP with integrated LTE and NB-IoT modem. And we make use of the NRF Connect SDK, which is the software development kit, and the ARM Cortex. So we have actually, let's say, deployed it. And thanks to Dutch Telecom and IoTCreators, not only for the invitation, but to allow us to do this. So thank you. What we did is that we deployed what you see in front of you. So as I said, we have a UDP application with Acklio solution, DTLS with SHIC. We implemented it in NRF 9160. We connected to a real NB-IoT network provided by Dutch Telecom, which provided us with the access for an IDD. And the IoTCreator is connected to Acklio's IP core, which is the SHIC gateway. Alex already explained it's the one that will do the compression and will handle it to security layers and the other layers. And what we did is that first we tested the connection. It went perfect. So we have a very nice connection, but we also wanted to see how much gain in terms of traffic. So the gain in terms of traffic is as follows. We have 3 setups. We have a standard one, which is DTLS UDP IPv4. This is the reference one in order to compare. We had DTLS over UDP over IPv4 with SHIC, of course, with an IDD. So what we did with the Nordic and IoTCreators with an IDD. And we have the third setup, which is with IPv6 and SHIC over an IDD. So compared to a standard DTLS UDP IPv4, we were able to divide the volume related to handshakes by 7, achieving around 86% of traffic reduction. We were also able to have a 74% of traffic reduction when using SHIC with an IDD. And to be able to imagine the impact is, let's take a case of 1 million meter commercially deployed in a network, and the traffic will be traffic reduction will be enormous, around 365 gigabits of data. So this is a lot, and this is a lot in terms of time of fair. This is a lot, knowing that the bitrate of NB-IoT, this will correspond to huge network capacity.
And just to add one thing, here of course we are comparing an already quite efficient DTLS UDP communication, right? If you take a TLS-based communication here based on TCP, the numbers are like completely off the chart, right? So that's also one point that's really important. So here we take something that's already quite efficient over IP, and we make it even more efficient, much more efficient over IP, and even further over non-IP. The important part here is that because of the way SHIC operates, IP or non-IP is seen in the same way by the device, like the meter, and by the servers. So the servers, they don't do anything special to connect to the device. Like they don't need to know any specific APIs or specific server address that they need to connect to. They have the IP addresses of the meters or of the devices, and they communicate over their natural language. So if we have a DLMS meter, it will be DLMS end-to-end.
Okay. So not only we wanted to check the traffic gain and the reduction, we also went a step further with Thales. So thanks to the support of engineers of Thales, we were able to implement Acklio's solution in the model EXS82W, which has LTE and NB-IoT capabilities. We leverage LGA DivKit family and a 9205 modem. And the objective is to see or to measure the power consumed and compare the cases with and without SHIC. So we use TII Arc by Quitec. So we can, of course, you can check always the slides to see the tools. We always reference what is used, like the Thales to the right, like Quitec to the left. And we used a similar architecture, thanks again to Dutch Telecom and IoTCreators. We tested how much energy is consumed. We had an experiment or several experiments where radio conditions are good. We used a payload of 50 bytes. In front of you is the architecture. So mainly we have the Thales board, the power measurement from Quitec, and we have the same to the right. So actually we leverage IoTCreators and we have the same one. And we consider the case of an IDD and the case of IP. So first, starting with the case of an IDD, the energy savings. So first I will start with the handshakes. So in comparison with a typical IPv4, shipped with an IDD achieves 76% of energy savings regarding handshake. With respect to the data transfer part, we achieve 90% energy saving. So of course, we're considering that we are sending like a message of 50 bytes, so it's a small one. In case of having, let's say, a typical DNMS with, well, we have, let's say, 100 or 200 bytes of DNMS, we can use header, not only header compression, but payload compression to further have the gains. Regarding IPv4, so we also compare with the IPv4 case. So in comparison with typical IPv4, Acklio solution, and here I'm talking about optimized shift with IPv4 and leveraging payload compression, we have 70% of energy saving for handshakes and 13% of energy saving for data transfer. So one point here is that here we are not using an IDD, it's IPv4. So what we are doing is that we are using SHIC to optimize DTLS, to compress IPv6 UDP headers and to compress some headers of DTLS and some payload. So we achieve actually end-to-end IPv6 communication. We compress, as I said, the DTLS header, and we achieve this amazing gain related to not only handshakes, but also data transfer. And also to imagine what is the impact. So consider that we have a DNMS meter, let's say a water meter, for example, that is each day, it makes one handshake for security, and then sends 5 times, let's say, a message of 50 bytes. We did this experiment, and what happened is that the power reduction we achieve in terms of transmission is 35%. So you can see that with a simple 5 data sending and 1 simple handshake.
So yes, well, so thank you very much, Hussein. And here one of the points when we talk about energy reduction, we are actually measuring the consumption on the whole communication module, right? So we are not simply like having some deductions of, okay, we reduce the payload of 70% or 80%, so we save 70% of energy. It's not the case. We reduce, you take the communication module, its use over the whole day, and it is 35% less by using these optimizations. Now here, of course, the point is, and all these results there, I think that they are very, very impressive, given that we do not change in any way, like the way the NB-IoT network was operating. So it's like only a software optimization that remains on the protocol layers. So we do not change the application, we do not change the head-end systems, we don't change the servers, we do not change the device applications. We do not change the network. We provide optimizations of the communication stack. And that's based on standard technology, on a standard compression framework. So what that means is that you can have all these optimizations across the different networks, IP or non-IP, across the different countries, independently of that, if that NTO, and actually in each country, your device will be benefiting from the specific optimizations enabled there. So if it's EDRX or PSM or whatnot, like the device will, the software stack will know when to sleep, when to wake up. It will be able to intelligently, communicate with the security layer, and all that compression will kick into place. And so this thing that like seems a little bit magical actually is completely hidden from the applications. It's completely hidden from the way actually you are going to be deploying your service, and you just get like 35% energy efficiency improvements. And that is for the good conditions, right? So here we have the results when the conditions are actually really good. And things will get, you'll get a much important, significant energy efficiency gains when conditions are not that good. Because when conditions are not that good, then over-the-air NB-IoT, of course, will repeat a lot of the symbols in order to get the necessary sensitivity, in order to get the signal out. And when you have reduced the data that you're sending like by 70–80%, then that reduction actually multiplies. So we do not yet have the results, but our internal approximations lead to a significant gain over these 35%. But of course, we don't want to speculate here. We will keep you posted whenever you have all these kinds of results in a much more specific way. And just to say that we do not want, of course, to keep you thirsty and to keep to hold you back. We want to give you all this so that you're able to start using it. So it's not going to be today, but starting very soon, starting 1st of November. You can go on to this link and register for early access to our developer program, which is already available for LoRaWAN. And what you get is access to a free, so everything is free, access to a cloud platform with up to 50 devices that you can connect, the libraries, so there's the SHIC firmware and libraries that you can flash on the different communication modules that you have, open source examples, and you have a DLMS example, so you can have a DLMS running over DTLS, running over NB-IoT in your home, and online documentation specifically crafted for for it to be like to have a guideline, really provide all the feedback that you need in order to be autonomous about this. So with this, I think that we spoke quite a lot. We have a lot of other things to say, but I think it's we'd like to hear a bit of if you have any questions, and that will be really nice. So.
Perfect. So thank you very much for this. You presented us some impressive results, and thus we have so many questions for you. So let me jump in chronologically. So is it correct that it is basically under the network layer? I think this question is for SHIC. Is it also possible to address? No, maybe you go first with the first question.
Yes. So. This is the very interesting part about SHIC. So SHIC is a compression framework. So you can position it at different levels, on different layers. And yes, initially it was really positioned just under the network layer so that you can compress IP, UDP, but you can actually SHIC can compress in one go IP, UDP, co-op, or anything. Like it's really not limited on the stack. You can go up to the application layer in one go. But yes, initially it was specifically positioned beneath the IP layer. Yes.
The follow-up question to that is it also possible to address the device, so do a two-way communication, so sending small data to device?
Yes, that is so. Today, SHIC is part of the internet. So it was standardized at the ITF, and it was standardized under the INT area. So it's the part about like standardization of IP connectivity, let's say. And in this part, like IP connectivity is like typically you need bidirectional communication. It's slower and so forth, asynchronous, no, not asynchronous, asymmetric. So, we'd like to have much more uplinks than downlinks, but it is possible to have bidirectional connectivity. Yes.
And yes, simply yes in the case of NB-IoT.
And it is simply yes in the case of NB-IoT. Thank you very much. Yes.
Yeah, all that matters. Okay, next question. Does this solution assume that all the population does support SHIC? Could the deployment be a mix of SHIC and non-SHIC without needing the AS to treat them differently?
You can perfectly well have a mix of SHIC and non-SHIC devices. You can have IP devices that do not speak SHIC, IP devices that speak SHIC as well, non-IP and non-IP with SHIC. And also you can have devices that are SHIC, that have SHIC as an option inside. And whenever they talk to an AS that is capable to talk SHIC to them, that can be a feature that it will activate, right? And actually we have the feature where you can configure remotely specific compression profiles so that you can know that, hey, well, these devices, they are talking DLMS, will run specific DLMS compression profile on them. And these others, they're talking lightweight M2M with OSCORE or something, and we'll be able to enable specific compression profiles for that.
Okay, thank you. Next question. Does it only work for UDP or also TCP too?
Okay, that's a very interesting question. So, I mean, the simple answer is it works for TCP, but it will be a little bit of a cheating if I stopped here, right? Because we can compress the TCP header, and that will work. The trouble with TCP is that it is connection-oriented protocol. So both ends need to send from time to time some messages just to keep the thing, hey, are you still here? Yes, I'm still there. And that's typically the thing that kills battery life, yeah, and that kills network, right? So this is where you would like to get things a little bit further away, where you can actually have proxies that will be terminating the TCP. I mean, you can do some clever things that you combine SHIC with some proxies that will keep the connections alive on the non-LPWAN part of the communication network. And on the LPWAN, you use pure SHIC, and then everything can sleep. The network can use the resources, the device can sleep, and you still have your TCP connections live, right? Of course, if you start from zero, or if you can afford, the best thing is to use UDP. But we live in the real world. In the real world, there are already many industrial protocols. There are many things that are already run TCP. So this is where we actually developed a solution for TCP over LPWAN as well.
Okay, thank you. So another topic. How many operators do you have worked with that have SCEFI for non-IP data delivery?
Oh, so this is a tricky question. I think that we have a bunch of NDAs that forbid us to give any number about this. What I can say is that
we can mention IoTCreators. So
yes, exactly. We can mention
Yeah.
IoTCreators, which are at the edge, at the leading edge in the world, right?
Thank you.
So that was a real pleasure. But of course, I mean, we have huge experience in many other non-IP connectivity networks, and we see that it's standards are important. If you don't do things in a standard way, yeah, you can build a prototype, you can set up a deployment, but down the road it doesn't work.
Yeah, but I want to add something here is that we test the solution over other networks. So
yes,
it's very important to say this. We will not tell more details, but we already tested.
Yes.
Okay. I believe this clarifies, I hope. I'm moving on with the next question. So does this solution requires to load a middleware on the device? Maybe it can be, how can we really integrate SHIC to our device? So
to really be able to talk about end-to-end IP and secure end-to-end IP connectivity, which is what SHIC is really all about, you need to have an embedded library on the device. So it can be on the communication module, and this is what we are doing with Nordic, with Thales, and others. So it can be there, and you can simply have some AT commands to use that directly. AT, and I mean you have, or you can develop on the modem itself, and you have like code like C functions to call. So that works there. It can be on the device, and we simply use the communication module like to send the bytes over the air. But typically, to have the full power of the SHIC solution, you need this. You need the library to be installed. Yes.
Thank you. Next question. The use case you described regarding the static IoT overhead assumes that every device is connected to E node B. What about a use case where more devices may exist underneath the device that is connected to the E node B? This may be a mesh with routing overhead. How much benefit do you think your solution could bring to such a use case?
It's a clever question.
Yes, I love this question. Right, and it's so thank you very much. It's I'm really impressed by all the questions. I'm very happy.
Same here.
Actually, I think that let me go with the short answer because I have tendency of spilling over. So the short answer is that SHIC there already works about SHIC over 802.15.4. So for mesh networks, so SHIC over 6LoWPAN, let's say. And you can apply SHIC to many different types of technologies, mesh technologies, multi-hop technologies, and the overhead that you're talking about. Well, you can solve that, right? You can have SHIC starting from your device that connects to the let's say to the gateway that will then connect to the E node B. So you have SHIC end-to-end between the device. Let's say it's, I don't know, it's a street light that connects over a mesh network. That then you have a hub that connects over 3GPP or over NB-IoT. So you can have a SHIC running from the street light all the way to your server, and you have end-to-end security, end-to-end compression. Or you may apply the SHIC on the gateway itself. Like you have the traffic that goes within your mesh network, then it goes in the hub that will connect to the 3GPP network, and then you apply SHIC. In which case you also have a lot of gains, because I mean you can have all your devices with their individual IP addresses, but the prefix typically will be the same there. So you'll be able to compress a whole lot of things in there. So I don't want to spend too much time on this question, but it's actually a really deep question, and there are many things that can be done like out of the box, and there are many other things that can be done if we spend some time on that question.
Thank you. Maybe they can follow up later on with this question. We have a lot more, so I try to be quicker. So which cipher suite do you use to get a handshake that's small, less than 300 bytes?
Oh, that is, I think, the most tricky question, because I will be able. I think that I will lie about. So I don't want to give you. Do you have
I don't know. The question is not very direct to me, because he's asking how did we get 300 bytes?
Yes, but which cipher suite? So I don't want to lie about the exact cipher suite. So I'll need to double check that with the team. So we use basically we use standard DTLS, yes, and we compress out everything, because in DTLS you have, in the handshake you have a lot of as you said, like cipher suites, and in the negotiation you have a lot of information that is sent from the device to the network and from the network to the device, and it's all the same. Like when we know the device, we compress that out, so we don't send that. And basically over the air we only have the nonce, and so the things that contain randomness in them, and this is down to 300 bytes. I need to check with the team exactly which one is we are using. But my answer to that is, typically it doesn't matter. The point is that the type of cipher suite the device wants, or the operator or the integrator wants to use, it is the one that will be used for when deployed in operation setup. And the thing is that all the bells and whistles around that are necessary for the handshake, they'll be compressed out. So you can imagine that SHIC is the thing that gets the pure randomness go from one send to the other. So all the things that are never repeating actually, and that's the only thing that goes out. So if you want to get down to how much bytes is going to, how well it's going to work for this or that specific cipher suite, you only need to look at, okay, in the packets, what are the random bits, and that's it.
Okay, there are some questions around DLMS. So one question is, the LMS is very chatty protocol. So is the SHIC, besides the compression, able to reduce the number of connections in the LMS?
Okay, so I'll answer this quickly. In the LMS, you have more than way to work. You have by based on request or session based, and you have the recommended for LPWANs, which is based on pushing the data. So the LMS meter would push the data into the hidden system and not wait for a trigger from the hidden system. So simply now with modern and the LMS, it's the meter that pushes the data into the hidden system, avoiding this chatty things. So the LMS is not very chatty when it's in push mode.
Okay.
Yes.
And a follow-up to that one, will you be supporting the LMS over narrowband IoT?
Yes.
The LMS over NB-IoT?
Yes, the LMS over
I mean, this is one of the clear messages that we want to send here. So yes, we have the solution and we want to go with it.
Yes, and you can come. So we'll be present on NB in Frankfurt at the end of November, beginning of December. So you can come and see everything in action, right? Yes. And you can start using it. As I said, I think it's the first of November that we open it on our developer program.
Yeah, it's exciting. I already sent the link to the developer program to the chat, so please check that one. And I continue with another question. Have you done power rate measurements with NRF 9160 using standard SHIC versus SHIC over non-IP data delivery, or any plan to do that?
We did not do the power measurements, but we are willing to, and once we have the results, we will share it publicly. So we will be very happy to share it later on.
Yes,
once we do it.
Thank you. Another question. Where is located the server that translates your protocol to standard IP protocol? Inside the network operator or just before your application?
Also a smart question.
Yes. So of course you can imagine that we'll be very happy the day that all operators around the world have that in their networks.
Yeah.
But until that day comes, you can run that server in the cloud and everything goes through there, or you can have an on-premise installation in your the location of your choosing. Yeah, I'm going to stop, but you are independent of the operator on that.
Okay. So Alexander and Hussein, do you have like 5 more minutes? We can complete the questions, or do you want to do them later? Okay, yes, then let's do that. I hope everyone has the time. Then another question.
Fast, but
yes.
Yeah. Could you shed some light on similarities and differences between SHIC and 6LoWPAN?
I think that this is a big subject, and if we want,
let me give just a word for that. So we designed SHIC because 6LoWPAN was not sufficient at the time, right? We started working that in 2012, and the initial works were about LoRaWAN. And the point was, how do you bring IP to LoRaWAN? And 6LoWPAN was just too power hungry. And the point of that is that 6LoWPAN is a stateless compression protocol. So, you know, hop by hop, and it's a very generic framework, works very well in many situations. But when you need to push the envelope, when you need to be able to compress down to 1 byte, the whole protocol stack, when you need to be able to compress application protocols, when you need to go down in the payload, right? Then it's out of scope for 6LoWPAN, but it's in scope for SHIC. Also, SHIC was designed specifically in mind for LPWANs to start with. So that means asymmetric connections. Asymmetric, that means that you can have potentially lots of uplinks and a few downlinks. So there is this asymmetric operation. We don't have a neighbor discovery with a lot of traffic, you know, all the time around this, and so forth and so forth. But these are maybe just the 2 big differences between these 2 approaches, which in some case can be combined, in which case you can have 6LoWPAN with SHIC compression. And then you have the best of both worlds for mesh networks. Right? But that's something that you don't want to have in star networks such as NB-IoT, NIDD or IP, and in which case, like SHIC is really the most optimal. From theoretical point of view, you cannot do better than SHIC. So yes.
Thank you for that answer. Another question, what about using SMS with encrypted content over LTE-M and NB-IoT? Is that possible? I guess this question is.
Oh, so I'll talk here something about our products. So you have the SHIC library that goes into the device, and you have a couple of header functions that you need to implement: send, receive, timer, schedule. And so we have the case of implementing over a completely different communication technology under a week. So I think SMS, there may be some caveats, but I don't see any problem to implement a solution in. I don't want to give a number because.
No, but theoretically it's possible. We can
yes.
do it. The idea is only to adapt it to the case of SMS.
Yes, exactly. Yes. So the short answer is yes.
Yes, good answer. So about the early access program, will it only be for narrowband IoT?
So the early access today, so today it's available for LoRaWAN. You can start using it today, right? And I mean, when you go to the IP core platform, for example, that's the core network, then you have 3 connectors for 3 LNS, the LoRaWAN network servers that are available. So starting, I need to check if it's on 1st of November or our R&D team are going to kill me and they're going to say on 5th of November. So this is why we say it's early November.
So let's say coming very soon.
Coming very soon in November. You have added another connector for NB-IoT LTE-M, right? So you can start using it today with LoRaWAN and just turn on the NB-IoT LTE-M functionality.
Okay, so not only NB-IoT.
Yes.
Another question, did you show the results for IPv6? Or do you have the results for IPv6?
Okay, so all results that we show are typically for end-to-end IPv6 connectivity on top of SHIC, right? And then this whole stack can run over NIDD or IPv4 or IPv6. So here we showed it under IPv4 for many reasons. One is that it's the thing that has been deployed. I think that we will be hard pressed to find an IPv6 deployment.
And over an IDD, you showed as
yes,
well.
and over IDD, yes.
Yeah, maybe in a few years.
Hopefully.
Okay, another question. At network level, the operators can deploy header compression from vendors like Nokia, Huawei, available features. What SHIC differs from those features?
Yes, so at the network level, the compression is ROC, so robust header compression. So you can look at SHIC as a 3rd generation of header compression. So ROC was the 1st generation, 6LoWPAN the 2nd generation, so they added different cases, and SHIC is the 3rd generation that is actually capable of doing everything that ROC and SHIC and 6LoWPAN does, but you can push it further down the road, right? You can push it, you can do more because SHIC was thought and designed as a framework. ROC and 6LoWPAN, they had like a very specific things to solve, and they are doing that brilliantly, right? But with SHIC, you can do more. So of course, I think that we are not yet at the size of Nokia, Ericsson, and Huawei. So you are not going to be able to have it at that level, at the operator level. But we hope that 3GPP and all these big companies will integrate that technology in their offering. Because I don't see any energy efficiency question here, but I just want to say that we have done the studies, and compressing 1 byte is 500 times more efficient than sending it over the air, right? So or in the core network and so forth. So for us, so starting from today or starting from standards, it takes time. But that is a technology that will be and has to be implemented in any wireless communication devices, just for the sake of energy efficiency and the sake of what's happening, around the world. So yes.
Thank you. So we have the last 2 questions. Could SHIC have effect on inner IP header in case of tunneling?
Yes, so SHIC can compress both. Like you can in one go. So if there is no encryption, in one go you can compress both the outer and the inner IP in case of tunneling. And I mean, this is basically what we're doing here with the encryption, so with the security layer, because DTLS is hiding what's happening inside, right? So we compress the outer part and the inner part. And if you have an IP tunneling where you don't have the encryption, well, in one go you compress both, and depending on the traffic, you can compress everything like both up to a couple of bytes.
Thank you.
Yes.
Lastly, does the fact that SHIC is stateful do affect its scalability? How many devices a single server could support?
As much as you want.
So
Very good answer.
that's of course the sales pitch, but so our IP core has been tested for, of course, not in a production, but has been tested for up to 1 million devices, and we have in roadmap 5 million devices, and that's with various SHIC, as you said, stateful. So we have the notion of a SHIC profile. So if you have 1 million different devices, each of them a different type, then you have millions SHIC profiles, and then it's going to be, a different story than if you have 1 million smart meters, for example, that have the same profile. But the way SHIC was designed was specifically to be very efficient. So if you look at the code for a device in a specific, very simple profiles, it can be down to a couple of 4 loops. So it was really designed with scalability in mind. So yes, I think that
no, theoretically, as much as we want, we can move from one or duplicate the service and so on. And the fact that we know how to optimize the implementation of SHIC in servers and how to use it to have the large number. We have our tests. So SHIC itself can be very scalable. That's what I'm trying to say.
Yes.
And thank you, Imad. A lot of interesting questions.
Yes,
Yes.
really.
Yes,
And
exactly.
Bruno.
Thank you, Bruno.
And thank you, Imad and Bruno, also for your feedbacks. And yeah, I think we are through with the questions. And as I told you, this was our longest session. So as I've also mentioned earlier, this was the last, but definitely not least. We saved the best for the end. So thank you so much, Alexander and Hussein, for this great session. Really, I'm very thankful that you joined and you shared your knowledge with us.
Thank you, Anisette. Thank you for the invitation and for all the support during our collaboration, because it is IoTCreator is a leader in what you do, and it's rare to have these companies that are also so open and that communicate in such an open way on such a technology at the leading edge. So we were very happy to work with you.
Thank you very much. Thank you. So with that, I would like to also finalize our NB-IoT and LTE-M Learning Week. And thanks everyone for joining. I started to see a lot of familiar names, and I'm glad that you were always there and joined us for our sessions. And again, I will upload, now it's my time to upload everything, and you will receive them very soon this week. You will receive everything that you need, and you can contact me or IoTCreators team anytime if you have any questions. And thanks everyone, and I wish you a great day, great rest of the week. Goodbye.
Thank you. Thank you everyone for your time. Goodbye.
Thank you. Bye.